This is Algebra 2, Lesson 113, and it's found on page 455. Okay, logarithms and antilogs. All right, to begin with, let's review the rules of exponents, because the rules of exponents are going to be the same rules that we use for logs, all right? So, if I had 10 to the 7th power times 10 squared, when I multiply and we have a common base, the base is 10, what do I do to the exponents? I add them. So multiplication is addition. That's 10 to the 9th. All right? So multiplication is addition. What if I had 10 to the 7th divided by 10 squared? That's division. When I divide and I have the same base, I subtract the exponents. That's 7 minus 2. That's 10 to the 5th. All right? What if I had 10 squared raised to the 7th power? A power raised to a power, we multiply. So it's 2 times 7, 10 to the 14th, okay? So remember, multiplication is addition, division is subtraction, power to a power is multiplication, all right? So what is a logarithm? A log asks, to what power do we need to raise the base such that it equals a given number? Okay? To what power do we need to raise the base such that it equals a given number? This is a log equation. The standard base for a log equation is 10. And what this asks is, when I raise 10 to the 2nd power, it equals 100, right? This value is your base. This value is your exponent. And that is what it equals. All right? Now there are other words for this. I'm going to rewrite it. Log base 10 of 100 is 2. Okay, so I just read it for you. Log base 10 of 100 is 2. That tells me that I must raise 10 to the 2nd power in order for it to equal 100. So what are we solving for? With a log, we are solving for the exponent. All right, that's going to be key for you to know. In log form, we're solving for the exponent, okay? This 10 is called your base. It doesn't change in logs. It's called your base. The 100, it's called your anti-log. Your anti-log, or your anti-logarithmic, okay? And then the 2, which is your exponent, is called the logarithm. All right? That's what we're solving for, the logarithm, okay? So when we have an equation in log form, we're solving for the logarithm, which we know as the exponent, okay? So always when we're solving for an exponent, then we're going to use logs, okay? It's important to note that your base can be any value except 1. The standard base is 10 when we're talking logs, okay? But the base can never be 1. So it cannot equal 1. Also, it's important to note that your antilog must always be a positive value. It must always be a positive value. All right? You'll never raise any value. 10, I could never raise to any value such that it will equal a negative number. Okay, it won't. And that negative number here is in the place of your anti-logarithm. Okay, all right. So how do we solve logs? Typically we do it in our calculators. Okay, so we use logs when we're solving for the exponent. Okay, so this is an easy example. All right, if I had 5 raised to the x equals 25, obviously we know that it's 2, x is 2, but I could rewrite this as a log, and I could say log, here's my base, 5, here's my anti-log, 25, and x is my log. And I could put it in my calculator. All right? So to put it in your calculator, when the base is not 10, okay, we're going to do one with 10 in just a minute. But when the base is not 10, it's this button right here in your calculator, and you enter with this button. You go in, wait, I have a 1 there. Let me clear it, okay? I put that button in. I put 5 for my base. And I move over. And for my anti-log, I put 25. And then I hit enter, and I should get 2. So when you do not have a base of 10, when your base is anything other than 10, acknowledging it can't be 1, right? You're going to use this button. Well, let's suppose that I had log of 50 equals x. 100% of the time when there's no base written, the base is 10 when we're using logs, okay? So 10 is the standard. We don't have to, it doesn't have to be in the equation if your base is 10, okay? So I can't just in my brain think 10 raised to what power is 50? I know it's between 1 and 2 because 10 to the first power is 10 and 10 squared is 100. So it's going to be a decimal point. All right, when I want to solve this log equation in my calculator, I hit the log button. And then I put my anti-log in, which is 50. And then I hit enter. And it gives me a decimal place. And we write the solution to 4 decimal places. So x equals 1.699. So 10, I could rewrite this in exponential form. My base 10 raised to the 1.699 will equal 50. And you can check yourself, okay? So I can do this with any value I can solve. Like I can do log base 4 of 64. What does that equal? I go to my calculator. Since the base is not 10, I'm going to use this button. And then my base is 4. My anti-log is 64. And then I hit equal. But I must have hit something wrong. Go back. Oh yeah, I put 64 in the base. I'm clearing that. I needed to move over. Try that again. Log base 4. Okay, now move over. Now I'm in the right place to put 64. So then I'll input 64 and equals. and it equals 3. Why? Because 4 cubed, in fact, equals 64. That's what that says. 4 cubed equals 64. That's the same equation as the log base 4 of 64 equals 3. This is in exponential form. This is in logarithmic form. Okay? Let's do one more in logs before we get to natural logs. All right, what if I wanted to know what the log of 105 equaled? Because there's no base written, I know that my base is going to be 10. This is asking me 10 to what power equals 105. Because my base is 10, I use the log button. Because my base is 10, I use the log button, and I just hit log, and then I input. I don't need to put 10 in as my base. I just put my anti-log in of 105, and I hit enter, and it will give me what the exponent is. So x equals 2.0212, going to 4 decimal places. So converting this to exponential is my base to my exponent. 2.0212 will equal 105. Okay? We're going to practice in a minute going back and forth between log form and exponent form. Okay? But a second part of this lesson deals with a natural log, all right? For a log, for this kind of a log, we have a constant, a number as our base, okay? So the base here would be 10. It's always a number. It's going to be log base 10, log base 4, log base 5. But when we look at the natural log, and back up one second, with the log, it can be any constant other than 1, right? This is called a natural log, okay? Its base will never be written because the base will always be the value e, okay? And e is a constant, much like pi is a constant, okay? So let's just look at the natural log of 105. Let's just see how it differs from the log of 105, all right? So to work this one in your calculator, let me clear now. You're going to hit the LN key, which is just below or just next to the log when you have a base 10. So you hit LN and then your value, 105. And what does it equal? That's your solution. It equals 4.6540. I can write this in exponential form because remember, in logarithms, we are solving for the exponent. This 4.65 is my exponent. In logs, we're solving for exponents. In exponents, we're solving for the anti-log. Okay? Logs, we're solving for the value of the exponent. In exponents, in exponential form, we're solving for the anti-log. Okay? I'm going to write this in exponential form. So my base is e. My exponent is 4.654, and it equals the anti-log, 105. Okay? So I want to walk through the practice problems. Actually, I'm going to first walk through some other problems, and then we'll work through the practice problems in the textbook, okay? All right, so what is the ln of 1.4? And then let's just do the log of 0.872. Okay, we'll just do these in our calculators. All right, natural log, I'm hitting ln. For my anti-log, I'm inputting 1.4, and I hit equal, and it gives me the solution. It equals 0.3365. In exponential form, let me move this one down. Log of 0.872. In exponential form, this natural log could be written as e raised to the 0.3365 equals 1.4. Okay? This one, my base is not there, so the base is always 10 if there's no base written. All right, but I can solve for that by entering log and then 0.872 is my anti-log and equals, and that's my exponent, negative 0.0595. Notice I said no negative numbers here in this place, in the anti-log place, but I can have a negative exponent because remember, negative exponents mean division, right? All right, so this written in exponential form is my base is 10 raised to negative 0.0595 equals 0.872. Okay, now let's practice a couple going back and forth between logs and exponents. Okay, so we'll do a couple both ways. All right, so we'll do the log. Base 3 of x is 9. We'll do the log. Base 2 of 8 equals x. We'll do the log. Base 3, 27 equals x. All right, we'll convert all these to exponential form so that you have a little bit of practice. My base is 3 raised to the 9th exponent equals x. So remember, when I said we use logarithms to solve for the exponent, we're always going to use exponents, the exponential form, to solve for the antilog. Okay? When we're solving for this value, the antilog, you're always going to convert it to exponents because I can put 3 raised to the 9th power in my calculator. Okay? The base for this one is 2 raised to the x power equals 8. Since I'm solving for the exponent, I absolutely would want to use logarithms, okay? Even though I know that 2 cubed is 8, right? There's going to be values you're not going to know. All right, this one, 3 raised to the x power is 27. All right, so that's going from logs to exponential form. Let's go the other way. Let's go from exponential form to logarithmic form. If I have y equals 3 to the 4th, if I have 27 equals 3 to the x, and if I have m equals 4 squared. All right, let's write all of these in log form. All right, it's log base 3, that's my base, right, of the solution equals my exponent. And then I want to do a couple of natural logs, okay? We'll go back and forth with a couple of natural logs. All right, this is log. My base is 3. My anti-log is 27 equals my exponent x. You getting this? The last one, log. My base is 4. My solution is m, that's my antilog, equals my exponent 2. All right, now what if I had ln of 10 equals x, and then what if I had e to the 5th equals y? All right, let's work both of these and go back and forth. All right, this is natural log form. My base is e to the exponent x equals 10. Okay, it's a natural log. Remember, e is just a value, much like pi. All right, this one, going to log form, be the natural log. I do not have to write the base, ever, for natural log, right? My antilog is y. My exponent is 5. All right, now let's work through the practice problems in your textbook. Okay. On page 457, 103.1, it says, use your calculator to get a value for e. Well, a value for e is just e to the first power, right? That's your value of e, because if you wanted a value for pi, you'd raise pi to the first power. All right, I'm going to show you where e is on your calculator. It's shift ln. Shift ln brings e to a power. And I just put in 1 for my power and hit equals. And it gives me the value of e. It's 2.718. Well, what if I wanted to do the same with logs? To get 10 as my base, I could hit shift log, and it would put 10 raised to a power, and I could raise it to any power. Okay? All right, so that's example 1. Now, 113.2 says use base 10 logs to simplify. All right, so we're going to have 47,832 times 59,463 divided by 0.000817. All right, what is this asking of us? I want 10 raised to some power to equal each one of these, 47,832. Okay? So we'll just work through this one. All right? So in the place of this number, I'm going to write 10 to some power, because then I can use my exponential rules to solve for this as 10 to the power, because multiplication is addition, division is subtraction. All right? When I'm solving for exponent, I'm going to logs. So this is log. My base is 10. My argument is 47,832. That's going to equal my x value, which is my exponent. So I'm just on the log of all of these numbers. So it's the log, because my base is 10, of 47,832. I hit equals. That's my exponent. So in the place of 47,832, I'm writing 10. I'm going to write it to 4 exponents. 4 decimal places. 4.6797. Okay? I'm going to do the same thing with 59,463. I'm just going to enter log and 59,463 equals. And it's going to be 10 to that exponent to 4 decimal places. 10 to the 4.7742. I'm going to do the same with this denominator. It'll be 10, it'll be the log of that value, 0.000817. And I'm expecting 10 to be raised to a negative value since it is so small a decimal. All right, so I just put the log, make sure I hit that right. 3 zeros, 0.000817, and I hit equals. And that is the exponent I'm going to raise it to. So it's over 10 to the negative 3.0878. All right, now I'm going to use my rules of exponents to solve for this as a power of 10. So it's going to be 10. I'm going to add those that are multiplied. 4.6797 plus 4.7742. I'm going to subtract that which is divided. It's minus a negative. Two negatives make a positive. So I'm going to add it. 3.0878. I'm going to add all of those exponents. Plus 4.7742 plus 3.0878. And this is 10 to the 12.5417. And I could solve it. 10 raised, right? 10 raised to the 12.5417 equals, and it gives me the value. It gives me it in scientific notation. All right. And that's the answer. They give you the answer in 113.3. It's 3.49 times 10 to the 12. 3.49 times 10 raised to the 12th power. Okay? Now, look at example 113.4. Okay? So, on 113.2 and 3, I could have converted those to logs with base 10. I could have converted them with LNs. It doesn't matter. Okay. So look at 113.4. What if I have negative 0.0325 equals log base E of Y? Okay, that makes no sense. You wouldn't have a log base E because if your base was E, then you'd have a natural log. Okay, I didn't write the textbook. I'm going to change it. Should be ln of y equals negative 0.0325. Okay? I'm going to convert this because I'm solving for the anti-log, right? I'll write it the other way so you can see it. It's the ln of y equals negative 0.0325. When I'm solving for the anti-log, I'm going to go to exponents. So natural log, my base is E. My exponent, negative 0.0325. And that is what y will equal. All right, so I can do that in my calculator. I hit Shift ln. That brings E raised to a power. I'm going to put in negative 0.0325. I hit enter. And that's my solution. That's what y equals. All right, so y equals 0.9680. So really, I could say, it should be true. The ln of 0.9680 should equal negative 0.0325. All right, let's go ahead and prove that. The ln of 0.968 equals negative, there we go. It works, you see? They're just inverses. Logarithmic equations are the inverse of exponential functions. Okay? Now look at 113.5. Last example. All right? So they give us the value of y, and they want to know what the log of y is. So y is 4302. What does that equal? Okay, what are we solving for in logs? We're solving for the exponent. What is that going to say? 10 to the exponent is going to equal 4302. So we're going to write it in exponential form afterwards. All right. And then they want the ln of y. So ln of 4302. What does that equal? Remember, the base, E, is really 2.718, some number close to that. So, you would expect this one, E, to a greater number than 10 to a greater number. All right, so we're going to solve. Log of 4302. I go to my calculator. I hit log. I enter that 4302. That's called my antilog. When I hit equal, that's my exponent, and it equals 3.6337. In exponential form, what does that say? 10 raised to the 3.6337 equals 4302. Okay? Now let's do the ln. Hit the ln button right here. ln 4302 equals, and that's the answer. It's 8.3668. When I write that in exponential form, because it's ln, the natural log, my base is e. Here's my exponent. 8.3668 equals 4302. Okay. We will talk about this on Friday.